How bright would the moon be if it was covered with ice and not regolith? How does spaghettification happen near black holes? How will the human body adapt to Mars gravity after the long journey? Answering all these questions and more in The Question Show. It's time for The Question Show. Your questions, my answers. As always, wherever you are across my channel, if a question pops into your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Larry Fields, how will the body adapt to Mars after 6 months, like when spacecraft come from the International Space Station? This has been an interesting question, which is that, if you are going to send a human mission to Mars, the astronauts are going to launch from Earth, they're going to spend 6 to 9 months in transit to get to Mars in zero gravity. Then they're going to land on the surface of Mars. Now they're in 1/3 Earth gravity. And we know that when astronauts come back from space, especially if they've been there for a long time, like when you think about, astronauts that have been on the station for a year, that they come back incredibly weak. Even though they've been working out, they can be very weak and require support. They have trouble standing up. They feel a lot of pain to just get up every day. It's really interesting when you read the biographies of astronauts who've spent a long time in space, just how detrimental it is on their body. And this is them working out every day and just sort of doing everything they can to try and maintain their muscles and their bone density. And so with Mars, it's going to be the same thing. They're going to be working out. They're going to be running, riding their bike, rowing, whatever it is they have to do on their spaceship to be able to get to Mars. And so one of the big questions was, when the astronauts arrive at Mars, will they be able to do the kind of work that will be required of them down on the surface of Mars? They're going to have to deploy their scientific instruments. They're going to have to set up their habitat. They're going to have to do all the various things they're going to have to do. And there was a study that came out about a year ago, and people looked at exactly this. They sort of measured the amount of muscle loss, bone density loss, how sort of weak astronauts who spent, say, 9 months in weightlessness, how capable could they be? And it turns out that it should be fine, that when astronauts actually do get down to the surface of Mars and then they do their work, they're going to be able to do that. But then the question I think you're asking is, like, what happens when they come back? So now they've spent maybe 30 days in Mars gravity, or maybe they've spent 18 months. There's sort of like, you have to decide which window you're going to do. You're going to do the 30-day version or the 18-month version. And after both of those times, then you get to come home the quickest, sort of cheapest way possible. And then you're going to do 9 months in transit in microgravity again. And that's starting to push longer when you sort of think about it. It's 9 months out. 1 month on Mars, 9 months back. That's 18 months in weightlessness. And then you have to come back to Earth and try to rehabilitate yourself. I'm sure it's going to be possible, like to stay for an extra 6 months over what astronauts have stayed is I'm sure reasonable on the human body. And they had that time on Mars. They could recover their muscles a little bit, but still, whoever goes to Mars is going to be putting their body into the death zone for 18 months. When they do this trip. It's not to be taken lightly, that you are going to be taking years off your life. Not just the time spent in weightlessness, but we know that there's long-term consequences for cardiovascular. A lot of astronauts lose eyesight, cancer rates, all of that time spent in high radiation. You are going to be taking years off your life to make this journey because you think it's important. And, I'm glad there are certain people that are willing to sacrifice that for that kind of an adventure and to push humanity farther out into the cosmos, but I wouldn't do it. Christian Desalier. Fraser, can you explain how the extreme gravitational field of a black hole causes spaghettification, and does this process affect all objects that cross the event horizon? Sure. So spaghettification is essentially tidal forces. So we'll sort of look at a less extreme version of this. So when you have, say, an asteroid that is flying past the Earth, there is a point where the asteroid gets closer and closer to the Earth, where the essentially amount of gravity that is experiencing on the close side of the asteroid is different enough from the gravity that's feeling on the far side of the asteroid that it overcomes the force holding the asteroid together. It depends on what the asteroid is made of. If it's a collection of rubble, then it's going to sort of smear apart. If it's made of rock or metal, then it's going to take more force to actually shear it apart into multiple pieces. But you're going to get this breakup of the asteroid into multiple parts. And then the asteroid is going to continue to orbit around the Earth. And then each one of these little parts is going to experience that same tidal force that's going to shear it into multiple pieces. And the same thing's going to happen. And then those pieces will get sheared apart. And then eventually you'll just have this sort of debris field that is orbiting around the Earth, and then it will all enter the Earth's atmosphere and the asteroid will be gone. And so when you think about a black hole, it's the same process. You are in orbit, let's say feet first, going around a black hole. And eventually, you're experiencing it like around a black hole. It is the most extreme gravitational well that the universe can craft. And so you're going to get closer and closer to the black hole. And at a point where the amount of gravity, the force that you're feeling on your feet is so much greater than the force that you're feeling on your head that your body chooses to be torn in half. That's better, right? That the force, the meat glue holding you together is weaker, than this difference in the tidal forces as you get torn apart into two pieces. And then those pieces get torn apart into other pieces and more pieces. And eventually you get broken up into this sort of atom thick stream of material that is orbiting around the black hole, and you go in. And the strength and the sort of the tidal shear that you experience depends on the size of the black hole. The smaller black holes, the stellar mass black holes, have a sharper gravitational well than the supermassive black holes. And so, you could fall through the event horizon of a supermassive black hole and not even feel it. You'd be, you're trapped and you're heading towards the singularity, but you wouldn't necessarily feel it because the gravitational well is very smooth, very gradual, inevitable, but gradual. While with a stellar mass black hole, it is sharp. And so you can be spaghettified as you go into orbit. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Low Res, Platinum Doodles, John Brady, Ciro Minacci, Larry Dingle, and Richard Lander. Join the club at patreon.com/universetoday. Countdown to Serenity. If a civilization could move a gas giant, could they ignite a star by moving one the size of Jupiter, perhaps one that is rogue, into a measurably dense gas cloud that hasn't created a star, bringing new light to the galaxy? So, stars are really just defined by the amount of mass in them. That if you have about the mass of Jupiter, you get a planet that looks very similar to Jupiter. Now, if you wanted to make the smallest possible star, like if you wanted to actually create a brand new star, then you would need to find 79 other Jupiters and crash them into Jupiter. You need 80 Jupiters to be able to make the smallest possible red dwarf star. So you're not asking, could you take a gas giant like Jupiter, move it potentially tens of light years to be able to find a gas cloud that you could then find more Jupiters. But I think, like what you're wondering is, could you then accrete material around your Jupiter to begin the formation of a star? And, astronomers actually aren't entirely sure what causes a star to form. That, stars come from these large clouds of neutral hydrogen, and that something causes that gas cloud to begin collapsing. So the one possibility is that you're going to have a supernova explosion go off nearby. The shockwave goes by, compresses material. That begins the process of star formation. We know that when you see the spiral arms in galaxies, those aren't actual arms. Those are density waves that are moving through the galaxy, kind of like waves on the ocean. As they move through the galaxy, they compress material together, expand it back out again. And wherever you see the spiral arms, they are filled with star formation from these density waves bringing this gas cloud material together. We get star formation when galaxies collide, that clouds of gas are colliding with each other and leading. But we're not entirely sure, like, what is the triggering event that causes most of the star formation? Is it supernova? Is it colliding galaxies? Is it spiral arms? And so, could you take a density of mass, move it into the kind of raw material that would lead to star formation, and would that begin a new star forming? And I don't know. I don't know if it's enough or if it's completely sufficient to begin a star. It'll continue pulling in raw material, increasing the size of it, heating up, gathering more materials. It gets more massive until eventually you have a new star. But you're really just kind of relying on the raw material. It's like if you climb up to the top of the tallest mountain, now you've made an even taller mountain. HR, how can we be in the center of a hot bubble where several supernovae occurred a mere 10 million years ago? That's a cosmic close miss. Yeah, so astronomers have looked at samples of material from the bottom of the oceans and found layers where it looks like iron was deposited into the atmosphere of the Earth that then sprinkled down, went through the water, and built up on this layer. And it tells us when supernovae happened in recent time. And actually, there's been a couple. One was about 3 million years ago, and one was about 5 million years ago. And we seem to be in this area. It's called the local hot bubble. And it looks as if there have been nearby supernova that have sort of pushed material out from our surroundings. And so, yeah, those are fairly recent periods of time. And it's entirely likely the Earth was bombarded by a relatively close supernova within the last few million years. And so if like two happen within the last 10 million years, then this must happen all the time, that a couple of supernova go off relatively close to the Earth every 10 million years or so, a few, tens of them every 100 million years, hundreds of them every billion years, 400 in the lifetime of the solar system. So this is a relatively common event. And yet when you look at the mass extinctions that have happened in the past, they don't happen, every 3 million years. They happen every few tens of millions or hundreds of millions of years. And so these supernova are definitely happening. They're relatively close. If you saw them, they would be as bright as the moon or brighter. And yet really a supernova has to be incredibly close for it to cause damage to planet Earth, like within a few light years, 10 light years, 15 light years, anything sort of farther than that, and it's safe. And the kind of damage that you get is not like the atmosphere is scoured off of the planet and our planet just turns into this smear, but instead you get a decrease in the amount of ozone layer, and so you get more radiation penetrating down to the surface, and maybe you get more evolution. So we really kind of don't know what impact, pardon the pun, various supernova had in recent memory. But yeah, there is clear evidence that supernovae have gone off in our recent geologic past relatively close to the Earth, which means it is going to happen more in the future. Gavin Robinson, if the moon was covered with ice, would a full moon be blinding? That's a great question. Now, I haven't done the math of like what would be, I believe this is a homework question. What would be the brightness of the moon if it had an albedo of 1, which is essentially it was reflecting all of the light falling on it. That is the albedo of planets like Europa or Enceladus, where they are almost entirely water ice on the surface and they are incredibly bright and reflective. People don't realize, but the moon is really dark, that, stand on freshly laid asphalt, that sort of black, sticky material. That's what it's like standing on the moon, like standing on charcoal. And we don't see that. Like when we look at it, we see this very light gray, and that's just because we're seeing the reflected sunlight coming off of this material. But if it was, like ice, it would just be incredibly bright. So I don't know how much brighter it would be, how many orders of magnitude compared to what we see already, but a full moon is already incredibly bright. Imagine if it was a lot more reflective. Thanks to everybody who put your questions into the YouTube comments, as well as everybody who joined for the live show. This was the one that we did in Canada, time stream, and following that was the Australian one, and so on. New schedule. I think I've mentioned this a bunch of times, but you should see the next event coming up here on the channel, and take a look at the globe and make sure you see which one it's going to be. Now I'm going to talk about a new show that I really like, but first I'd like to thank our patrons. Thanks to Abe Kingston, Adam Shaver, Andrew Gross, Barry Lake Roofing, David Giltonan, David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, Spiderswap.io, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So every now and then I tell you the television shows that I'm watching that I'm really enjoying, and I will only tell you the shows that I love, like the 10 out of 10s for me, and not the stuff that I'm, it's fine. And so the show that I really enjoyed this week is Secret Level. And if you don't know what that is, this is sort of like a sequel to what is probably my favorite show on Netflix, and that's Love, Death, and Robots, which is sort of a series of science fiction, short stories, animations that are on, in many cases, they're like written by science fiction authors, and then they've turned them into these short animated things. And they're so good. Like every couple of years, I just rewatch the whole series again and again. And the team behind it has come up with a new series that is on Amazon Prime called Secret Level. And the gist is that they are making a short animated film about a video game. And I'm not sure like how this will, what's the deal, who paid who for this, but they made a horror short film about Pac-Man, and it's gripping. It's really good. They made a Warhammer 40K video. There's one on Dungeons and Dragons. So, and so far they've got 8 out. There's a bunch more coming, and I highly recommend it. I really enjoyed it. So if you have Prime or you have access to it, definitely check out Secret Level. All right. We'll see you next week.